Well, hey there. Good day, everybody. Well, I'm getting ready to go off to a library in the neighboring community of Rio Rancho, New Mexico, next to Albuquerque. And I need to make sure I bring this because I'm going to do a talk about the abacus. If you remember, in April of this year, I had an exhibit of items from my abacus collection at the library in Rio Rancho, and they invited me to come back in the fall to do a talk about the abacus. So I have to go out there today. It's about 10 minutes before we have to leave. I just got my entire plastic huge box bin of my collection of abacuses. I have my PowerPoint presentation on a thumb drive, and I forgot I need to bring that guy as well. This is my teaching abacus. They use these in schools in East Asia. If you know what number that is supposed to represent, leave a comment down below. Okay, so this is the collection of abacuses. And luckily I gave myself plenty of time to get there because we have construction. Well, I'm only 45 minutes early, but at least I got here in time. Well, so here we are. I am all set up with the abacuses and the PowerPoint presentation, and we have one visitor, at least, plus my wife, so at least we'll have two people listening, if not more. I'm Joe Van Cleve. I am an abacus collector and aficionado. We're going to go through the history of the abacus, the different types of abacuses, and basically how they work, and look at some of the examples in my personal collection. So the abacus, what is it? Well, it's an ancient calculating device using either beads strung on rods in a wooden frame or counters placed on a board or table, and they date very far back in human civilization, maybe as far back as 8500 BC or earlier. So in the beads on rods version of the abacus that we know of today, each rod is assigned a place value, and each bead on that rod has a value depending on its position on the rod, how it's moved, in other words. There are three main types of abacus still in use today and still being made. The 10-bead or Central Asian or Russian abacus, which is known in Russian as something like shati. And then there's the 2-5 abacus in China that's known as something like swanpan. And then the 1-4 abacus in Japan known as Soroban. And the 10-bead version of the abacus, the Central Asian version, uses strictly decimal notation or decimal grouping of beads, whereas the other two that use upper and lower beads, the 2-5 and the 1-4, use what's called quinary grouping, which is similar to Roman numerals. Okay, as we said, the abacus dates as far back as 8500 BC, and it's derived from early man's finger counting and drawing in the sand in order to count things. The abacus was used in ancient Greece. The version they had was the counting board, and Rome inherited the counting board version of the abacus from Greece, and they spread it over Central and East Asia and what became Europe over the last 2 millennia. The ancient Greeks, their version was a table or tablet with lines, all lines denoting place values, and they used counters, which could have been cast from or molded from clay. They could have been carved out of wood and also minted out of metal. And this, of course, is called a counting board. In fact, the word abacus is a Greek word that means a flat table or surface. So when the Romans adapted the Greek counting board, they also developed their own handheld abacus, made out of clay that had grooves and clay balls that rolled in the grooves. And the Roman counting board version that they got from Greece was adapted in Europe after the fall of the Roman Empire, and it was used in Europe by banking houses, noblemen, tax collectors, etc. And they typically used counters that were minted on the front side with an insignia of the bank or the house or the nobleman or the king. And typically the back side of these counters was not cast or not minted with an insignia. And then the counting board in Europe was used up until the 18th century. It was actually taught in schools up until the 18th century, so fairly recently. I might also add that the terminology we use today, we have a checking account and we have checks that we write. Well, the word check in reference to the checking account comes from the exchequer, which is referencing the table, the counting board table used in European banks, a large wooden table with a grid of columns and rows upon which counters, or jetons in French, were cast in order to count and add up sums of numbers. So your modern checking account, the terminology comes from the European counting board. So around the 12th century, through trade routes with East Asia, with China, the Roman abacus, especially the hand abacus, is adapted into East Asia, into China, and then they soon change it to become the construction we know of as beads on rods, rather than clay balls rolling in grooves on a clay tablet. And around the 16th century, the Chinese 2-5 abacus was then adapted by the Japanese culture, as they did a lot of Chinese culture, and they soon got rid of the extraneous upper bead and they made it into the 1-5 abacus, which they called Soroban. And then in the early 20th century, due to the rapid mechanization of Japan as an industrial power, they modernized the abacus, their version, into the 1-4 Soroban, where you can represent the digit 0 through 9 on each row, in keeping with modern science and engineering. Well, there is this Asian 10-bead abacus, otherwise known as the Russian abacus. There is a close-up of it on the left picture here. And, of course, in Russian, it's known as the word pronounced something like shati. And it was taught in most Soviet-era schools up until the 1990s, but even today it is still used in parts of Russia and Central Asia in stores alongside electronic cash registers in retail commerce. In fact, you can see videos on YouTube of merchants using electronic cash registers to add up items from a customer's purchase, and then they will go right over to the Russian abacus and add them up on the Russian abacus as well. So it was related to the medieval counting board, and which was derived from the Roman counting board, and we suspect that there may have been some cross-pollination of ideas coming back from East Asia, from China, where they get the beads on rods construction. So the Russian abacus, the rods are arched, so that when the beads are moved from one side to the other, they stay put where they've been moved to. Now, you might recognize the abacus on the right side, the right picture. It looks kind of like a school children's abacus. This is an old one that may have been French of French origin, because in Napoleon's invasion of Russia in the 1820s, one of his officers was taken prisoner by the Russians. His name was Jean-Victor Poncelet, who was a famous mathematician. And he discovered the Russian abacus and its common use in Russia, and he brought it back to France after the war, where it became the school children's 10-bead abacus. And eventually that abacus was adapted into America as the child's toy abacus, which we see today in toy stores, etc. And we typically don't teach kids much, unfortunately, how to use the abacus other than to play with the beads and drool on them. So it is considered, the 10-bead abacus is, the easiest form of abacus to learn. So then we have the Chinese abacus known as the swan pond, and it has 2 beads on the upper part of each row, each rod, and 5 beads on the lower part, which is why we call it a 2-5 version. Each bead on the upper half counts for 5 of that place value when they're moved toward the rod or toward the dividing bar. And each bead on the lower half of each rod counts for 1 as they're moved toward the dividing bar. So you can see that there is a total of 15 that you can represent total on each rod, which seems like an excessive number to be added on each row, since in common decimal number systems we only need the numbers 0 through 9. The reason why you can count up to 15 on each rod is because the old Chinese currency was base 16. So they used each rod as a denomination of currency, and so they needed to be able to count up higher than 9 on each row. And also there was an early form of division that they used, and it was called iron division, and you needed extra beads on each row in order to do it, which is why you needed more than just 9 on each row. The Japanese adapted this abacus in the 16th century, and they quickly turned it into the 1-5 Soroban, which we'll see in a minute. This abacus is still being used in parts of China and East Asia, and they're still being manufactured commonly as a tourist item. So the Japanese Soroban, you can see there's two versions I'm showing here. The one on the left is the 1-5 version. This is the older version, very similar to the kind that Japan had been using since the 16th century up until the 20th century. And then in the early parts of the 20th century, due to the rapid industrialization, they got rid of the extraneous fifth bead to make the version on the right, the 1-4 Soroban, which enables you to count from 0 to 9 on each row, just like we do with modern base 10 number system. You'll notice the abacus on the left has kanji character on the dividing bar for each rod, and these are denoting denominations of yen. So the history of it, of course, comes from the Chinese abacus. Early 20th century, it was converted from the 1-5 to the 1-4, although the 1-5 version is still being made and used because there are some people who are, in their own cultures, it is traditional to have the 1-5 abacus. Just like in China, they still make the 2-5 abacus, but when they use the abacus, they're typically only using the numbers up from 0 through 9 on each row. So one thing that's notable about the Japanese Soroban is that it has the highest level of craftsmanship and artistry in design and construction. And also, in the early 20th century, they began teaching Soroban in schools, and they developed a competitive ranking system similar to martial arts called the Dan ranking system. And they developed a system of officially licensed Soroban operators where you could get a job as a Soroban operator, educational ranking or capability was high enough. So then, because the modern 1-4 Soroban only has 5 beads on a rod, and because the human mind can generally picture or imagine 5 objects at the same time, the Japanese in recent decades have developed this system called Anzan, which means mental abacus. So here, with mental abacus, students are actually not holding a real abacus in front of them, but they're actually mentally picturing the beads on an abacus, and they're moving their fingers. And students who are able to develop mental abacus or Anzan to a high degree, they can add up 9 or 10 or 11 digit numbers in rapid sequence with hardly any effort at all. And it's just amazing to watch them. And so this is the modern development of the abacus. It is the mental abacus. And also, the Soroban has spread from Japan into Taiwan, Singapore, South Asia, India, anywhere there is a strong interest in education for their children. There are abacus academies, after-school abacus academies that parents enroll their kids in to help increase their mental capabilities, even in some Asian communities in the United States. And also, the building and use of the Japanese Soroban is considered an important Japanese cultural art form. So what kind of calculations can you do on an abacus? Well, you can do addition and subtraction. Those are the easiest calculations to perform, and if you're trained, you can generally do them almost as fast as an electronic calculator. But you can also do multiplication and division, and there are several methods of doing these. Some are older methods, such as with multiplication is repetitive addition, or with division is repetitive subtraction. But there's also the more modern methods of multiplication and division that were taught in the 20th century, which is similar to the way we do the paper and pencil version of multiplication and division. But there are people that are now interested in doing things like square roots and cube roots and other advanced calculations, mainly as a novelty to challenge themselves to see how sophisticated of a mathematical computation can they do on an abacus. So why use an abacus instead of a calculator? Well, that's really not the right question, because it's not really a matter of using instead of, but typically also along with a calculator. And what I mean is the abacus is best suited for addition and subtraction, and if you train yourself, you can use it just about as efficiently as an electronic calculator. The difference being that using an abacus is typically more fun than using an electronic calculator. And because of the experience of the Asians of teaching children the abacus, it appears like they do help children become smarter in their education. It helps their minds grow faster. And also, the operation of the abacus, fingers on beads, and the clicking sound of the beads is very calming in a classroom environment. So there's kind of a calming effect and a internal focus that the abacus brings to people. And also, there's an historic connection with the abacus going all the way back into the early periods of human history. So there's a historic connection with our humanness by using the abacus. And also, using and collecting them, they are beautiful objects. Well, we talked about the Greek and Roman and European counting board as one of the simplest forms of abacus, and I'm going to show you how it works here. So the counting board is simply a grid of columns of place values. And you have here, I'm representing standard decimal place values. The Romans would have used Roman numeral place values, but it's pretty much the same. And the counting board does use what we call quinary grouping. And what that means is, here I've cast some counters onto the ones column on the right side here. And the three counters that are on the line represent one each, or the value each of the place value, whereas the single counter in the space to the left of the line counts for 5 of that place value. So again, the counters on the line each have a value of that column. Counters in the space to the left have 5 times that value. These 4 counters that I've placed, what number is represented? Well, of course, it would be 8, right? A 5 and 3 1s. So that's how you represent an 8. So what I'd like to do is show you how addition works on the counting board, because it's really fundamental to understanding all the other forms of abacus. So we're going to do a problem involving adding 2 3-digit numbers together, and the first step is to enter each number on the abacus. So we're going to do the problem of 123 plus 456. So here is 123 entered, 1 of the hundreds column, 2 counters on the tens column, and 3 counters in the ones column. And then below that, in its own separate row, we're going to enter 456. And you notice I've denoted a little dotted line, just separating the 2 numbers. Well, on some of the European counting boards, it was actually a grid on the board. And the horizontal lines just helped you separate separate numbers. So here we have 2 numbers laid out, 123, 456, and you could add more numbers below these if your board was big enough. But the second step of addition, and oh, by the way, you don't need to know how to perform addition. What I mean is you don't need to memorize an addition table in order to use the counting board. That's the beauty of it. So the second step is called grouping the numbers. And so for grouping the numbers, we simply push them all the way up, keeping them in their same columns, but we push them all the way up until they're one set of grouped beads or counters. And then the third step is the most crucial part of it, and it's called rationalization. Rationalization is reforming these groups of beads so we can read them off as a standard number. And there's really two steps to it. We start from the rightmost column moving left, and if there are 5 counters on a line, we take them away and add a counter in the space to its left. And the second rule is if we have 2 counters in a space, we take them off and we add 1 counter on the line to its left. So if we analyze this problem with those 2 rules, we find, starting from right to left, the ones column looks good, the tens column looks good, but the hundreds column has 5 1 counters that we have to move off the board and substitute with 1 single counter in the space to its left, and this gives us the answer of 579. So let's go ahead and add the 456 to this new number. So 579 plus 456. So we're going to enter our 456 below that. That's the first step. The second step is to group the numbers together. We push them up, keeping them in their individual columns, right? And then the third step is regrouping. And here we start at the very right. We see there are 5 counters on the line. We have to take them off the board and substitute them with a single counter in the space to the left. And then we now have 2 counters in the space, and we have to take them off and substitute them with a single counter on the next line to the left. And now in the tens column, we also have 2 counters in the space. We have to take those off and substitute them with a single counter on the 100s line. And then those 5 come off and they get replaced by a single counter in the space. And finally, these 2 come off, get replaced by a single counter in the thousands line, and it forms the answer of 1035. So we didn't need to know addition in terms of an addition table. We didn't need to memorize any addition. All we needed to know how to do was how to represent numbers with counters, how to group them, and how to rationalize the result. And that's the beauty of the counting board, is simplicity. We find that there are therefore 2 different kinds of abacus. There's the beads strung on rods, the common kind we're familiar with today, and there are the counters, the counting boards. And the advantage of the counting board is really that there's an unlimited number of counters available to be used. It depends on how many you're carrying with you in a bag or a sack or whatever, but numbers can be directly entered, then combined, and then the results rationalized. And this process is very easy to do and easy to understand. It's a little slower in actual operation than the bead on rod abacus. But one of the vital things about this kind of abacus is that all the operational steps are visible to an external observer. There's nothing mentally performed. Everything is performed in the open, so there's a sense of trustworthiness with using the counting board, which is very important in cultures where different parts of the culture didn't trust each other very much back then. Whereas the beads on rods abacus, you have a fixed number of beads available on each rod, which means there are times during the calculation that you need to use complementary operations when you run out of beads in the middle of a calculation, as we shall see shortly. And therefore, the beads on rods abacus requires more work and more mental work, but also can be faster. The modern 1-4 Japanese Soroban type of abacus, and let's look and see how numbers are represented on it. First of all, you have a single bead above the dividing bar on each row, on each rod, and 4 beads below. Each upper bead counts as 5 when they're moved toward the bar. Each lower bead counts as 1 of that place value when they're moved toward the bar. And beads only count their value when they're moved toward the bar. So if you look at this illustration, the blue colored beads currently do not count any value because they have not been moved toward the bar, whereas the yellow beads do count their value. Now, I would ask you, if you want to look at these beads, the yellow ones, reading from left to right, can you read what the number is? It is 1, 2, 3, 4, 5, 6, 7, 8, 9. It's the representation of the numbers 1 through 9. And you'll notice the 6 through 9s are composed of a combination of 5 beads and 1 beads, or upper beads and lower beads. So that's how numbers are represented on the Soroban. There are 2 general methods for addition with any bead frame calculator or abacus. There's the modern method, which is the number entry method, but there's this older method called the counting method. And the beauty of the counting method is you don't need to know addition or any addition tables, and you really only need to know how to count from 1 to 9. So let's look at that as opposed to the direct number entry method, which is the modern abacus method, which involves complementary operations oftentimes, is faster to do, but it's a little more mentally harder. And also there are some mental steps involved which may not be transparently obvious to an external observer. So there's an issue of trustworthiness with the direct number entry system. So let's use the Soroban and use the counting method, the easiest form of abacus, the easiest technique of using an abacus. So we're going to do the problem of 6 plus 7. Now this particular problem I've chosen specifically because if you were using the modern number entry method, you would find that this is rather difficult without knowing some tricks. But on the direct counting method, we first simply enter 6, which means we're going to move a 5 bead and a 1 bead toward the dividing bar. And now to enter the 7, you'll notice we don't have 7 beads left in that first row or the first column, but we're not going to worry about that because we're doing the counting method, and it doesn't matter to us with the counting method. All we're going to do is we're going to count up to 7. We're going to count from 1 to 7, and each number we're going to add a bead as we count. So we're going to start here. Our count is 1, and then 2, and then 3. And now watch this. 4, we simply clear out that column and add that bead onto the next column to the left. Continue 5, continue 6, and 7. And our total, therefore, is 13 is what we read on the abacus. So it's a very straightforward method. There's no addition tables to memorize. You only need to know how to count from 1 to 9 and how to regroup when you run out of beads on a column. It's a very simple method, and people have been doing this kind of method for thousands of years. So now there's an issue. The counting method works well in verifying trust between merchants and customers, or between different parties in a transaction who intrinsically may not trust each other, because the second person observing the calculation can observe and understand every step of the process. They can see each bead being added one step at a time. There's no hidden mental steps involved that an external observer wouldn't be able to spot. And so for this reason, the older versions of the abacus that have redundant beads, like the 2-5 and the 1-5 and the Central Asian 10-bead abacus, historically these work better or have been used more often with the counting method. Whereas because of the 20th century Japanese industrialization phase, it brought the need in Japan for speed of calculation, it being more important than social trust. Hence, the development of the 1-4 Soroban and its refined techniques used today. So again, the more modern methods of direct number entry require more mental operation steps, which means you can't externally verify the calculation as easily. So let's see how this direct number entry method works with the Soroban. So we'll look at a number of problems, but the simplest one is going to be 1 plus 3. Here we have the Soroban. The beads have been cleared away from the dividing bar. And now we're going to simply add 1. First of all, our first number, we're going to enter 1 toward the dividing bar. And then we're going to enter 3 more beads for a total of 4. Very easy, obvious problem. No complications required. But there are some times when we are adding two numbers together, we run out of beads. The necessary way to get around this problem is to use what are called complementary numbers. And so we need to kind of understand what these are before we go any further. So because we will sometimes run out of beads when we're in the middle of a calculation, we have to use complementary numbers. Sometimes the numbers we're dealing with are smaller than 5. In that case, we use what are called 5's complements. And all it means is instead of adding, for instance, the number 1, its complement is 4, or the number 2, its complement is 3, etc. But there's also complements with respect to 10. For instance, here, the number 1's complement would be 9, and the number 2's complement would be 8, etc. And the way we use complements in these kinds of problems is if you cannot directly add the number or enter the number, then you, instead of adding a number, you subtract the complement of that number and then add a single bead onto the next higher unit. So we're going to look at an example of this, 3 plus 4. Okay, so here is our sample abacus rod. We have 3 beads we're going to enter. So step A, we enter 3 beads, and now we're going to try entering 4. And you'll notice we don't have 4 1 beads left on this rod to enter. So since we don't have enough beads to enter 4, instead we're going to subtract the 5's complement of 4 instead of adding 4. So instead of adding 4, we subtract 1, which is the 5 complement, and add a bead on the next higher unit, which is our 5 bead above it. And so it works like this. And that's the way the calculation is performed. You move down the 1 bead as you're moving down the 5 bead, and you form the answer of 7. This kind of a problem is called a 5's complement problem. Now, there also are other kinds of complementary problems that use this same rule, and one example is 8 plus 3. So again, we're going to enter the number 8 onto our abacus. There we are, 8 has been entered. And now we're going to enter the 3, but we find out we don't have 3 1 beads left on that rod to add. So what do? Well, our complementary rule says instead of adding 3, we subtract its complement. Well, the complement of 3 in this case is 7. The 10's complement of 3 is 7. So we're going to subtract the complement of 3. We're going to subtract 7 right here, right, which is a 5 bead and 2 1 beads. And then to finish the problem, we add a bead on the next higher unit, which is the next row to the left, like that. And that gives us the answer of 11. 8 plus 3 is 11. So there are also problems with complements that not only involve 5's complements and 10's complements, but they involve both 5's and 10's complements in the same problem. And this is that problem 6 plus 7, which we did earlier on the counting board, and it was very easy on the counting board. But let's do 6 plus 7 on the abacus here. So we start off with 6, a 5 and a 1 bead. We enter the 6, very easy, right? And now we're going to add the 7. Well, we don't have a 7 beads left on that rod, so we know that we now have to subtract the complement, which is 3. We have to take away 3 to do our 10's complement problem. However, we don't actually have 3 1 beads to take away. So what we do instead when we get to this point is there is a rule that Japanese Soroban experts have developed, which is when you get to this problem and you can't directly finish the 10's complement, you do what's called push the number up. The number we're adding is 7. And so instead of doing the complementary problem the other way, we're going to push 7 up. And 7 is composed of a 5 bead and 2 1 beads. So we're going to push the 7 up, and then to finish the problem, we add a single bead on the next higher unit, which is the next rod to the left. And that gives us the answer of 13. 6 plus 7 is 13. And this is known as a combined complementary problem involving both 5s and 10s complements. So there's 4 different kinds of problems that you might ever encounter in a Soroban. So if you look at the blue vertical column in the middle of this chart, those are all the possible numbers you could be starting with on the abacus, 0 through 9. And then the teal-colored row above represents all the possible numbers you could be adding to it. And the intersections of all those possible numbers, the chart tells us what kind of an operation we have to do that calculation. So direct number entry problems like 3 plus 6 or 2 plus 2 or 7 plus 2, they're in white. If it's a 5's complement problem, they're in yellow. If it's a 10's complement problem, they're in green. And if it's a combined 5's and 10's complements, those nasty problems, they're in the salmon color. And you might notice this kind of symmetry, this diagonal symmetry between the upper left and the lower right half of the chart, which is kind of an interesting mathematical oddity. But in actual operation, a Soroban operator doesn't really think about memorizing this chart. That's not actually the mental process. Here's the mental process that I go through when I evaluate an addition problem. I ask myself 3 different questions, leading to 4 possible answers. So the first question I ask myself is, can the number, now we're talking about the second number. We already have a first number on the abacus. We're talking about entering the second number, which is addition. The first question is, can the number be directly entered? If yes is the answer, then enter the number. Congratulations, you've solved it. But if no, then go to step 2. So step 2, the next question you ask yourself is, are both numbers less than 5? In other words, the starting number that's already on the abacus and the new number you're adding, are both of them less than 5? If yes, then do the 5's complement. Subtract the 5's complement of that second number and then enter a 5 bead. And then you will have finished the problem. But if no, if both numbers are not less than 5, then go to the third question, which is, can a 10's complement be subtracted? So can the 10's complement of the second number you're entering, can it be subtracted from the beads that are already entered onto the abacus? If yes, go ahead and subtract it, and then enter a bead on the next rod to the left, and then you finish the problem. But if no, if you cannot subtract the 10's complement immediately, then push the number up. Remember, we pushed the 7 up. Push that second number up and then enter the bead on the next rod to the left. So we find in 3 questions we can interrogate any problem and come up with 4 possible responses. We either enter the number directly, we either perform a 5's complement, we either perform a 10's complement, or we do the pushing the number up, the combined 5's and 10's complement. And that's kind of how I evaluate any problem on the Soroban. Well, the presentation's over, and it was really fun. This was my first time doing it in public, and there was a lot of good questions. People really wanted to know where they can get a good abacus with large beads and a good, simple book on how to use it. So that's what I'm going to find for them next time I do this. And this abacus right here turned out to be very popular. So, my dear, how do you think the presentation went?
I think you did very well. People were really interested, got some good feedback afterwards.
Good. And not too many people were yawning or falling asleep?
None of them did. Nobody yet nodded off.
All right. That's good. Well, it went really well. Had great assistance by the library representative who helped set up the meeting. The challenge in doing this kind of a talk about some strange subject matter like the abacus is you don't really know who your target audience is yet and what their interests are going to be like. So I included a lot of things about the history of the abacus, all the different versions, how they all kind of worked, and I gave examples in the PowerPoint presentation about how the counting board version works in the old Roman and European counting board, as well as the modern abacuses that we know about from Japan and China and Central Asia. So a lot of different stuff, but in the end, I think the hands-on part of the demonstration was a lot more interesting to them, really just being able to get their hands on them, manipulating the beads. And then there was one lady in particular who had really a lot of good questions about. She really liked this teaching abacus over my shoulder with the large beads that stay put. They don't move around too easy. She wants that kind of an abacus for herself, and so we looked up on Amazon where to find one, and she also was interested in getting a really simple book that starts off with how to basically do addition. Anyways, it was a very good experience, and it helps me if I want to go and do this presentation again in the future. I certainly kind of know how to tailor the presentation more toward what I might expect people are interested in. Certainly the hands-on part of it is going to be more interesting than things like history, but there might be some people that are interested in the history of numbers and stuff also.